bending stresses and bending shear stresses and bending strain in the last few classes. Today we are going to see one or two example problems to get ourselves accustomed with what kind of problems it can come and how do you solve this kind of problems. So I've taken two problems. One is from the design perspective and the other one is normal analysis kind of problem. Okay. The problems that you will get will be of two kinds. As I said, one is analysis where you will be given the beam properties in the beam geometric properties. You'll be given the load and you'll be asked to find the maximum shear stress and maximum shear strain. Sorry, maximum shear stress and maximum bending stress. Right. So that's one way of looking at the problems. The other way of looking at the problems is some of the cross-sectional properties of the beam is not given. Let's say the depth of the beam is not given. Okay, in that case, it will be asked that given a loading, what should be the depth of the beam for it not to cross maximum design stresses in shear as well as in bending. So that kind of problem is called design problem, where you design the cross section of the beam. Okay, so that we'll also see today. But you can when you do problems, when you solve problems, please look from both the perspective what what makes what kind of sense. All right, so we are left with two things. One is composite beams, which will start tomorrow, and strain energy of in bending that may be in the next week, and that will follow with the deflections of the beam. So next week is already, oh my god. So next week we will start with deflections of beams. So once we cover deflections of beams, we'll come back to unsymmetric bending and columns. Okay, we will see whether we can cover unsymmetric bending. At least I will take one class on unsymmetric bending. That makes the understanding of bending easier. That may not be part of syllabus because other three professors may not cover that, but we will touch upon it. All right. So sign conventions are very important, and you should always, when you solve a problem, you should always take the sign conventions that are easy for you and that you have practiced well. So this is the sign convention that I consider positive for my analysis, and this is negative. Okay, so shear going up on the left plane, shear going down on the right, and sagging kind of movement are my positive considerations. Before I go into this part, let us understand what kind of geometry. Yes. Yeah, these are various sections, different kind of sections that are used in design of beams. Okay, this is a rectangular section. So square will also be part of this. Then this is called I section. This is, I don't know, this is double I. This is T section. This is box. This is channel or C. Okay, this is again I. Now, why these kind of sections are used? Now, Indian codes gives you a design guideline where you have a design book where these sections are given with their properties. Okay, so when you look into engineering, we don't make all kinds of dimensions, right, for member sections, right? So you can, for example, what I mean is this wave has a thickness, right? Let's say this thickness is 10 mm. If your design requires a thickness of 10.5 mm, you may not get 10.5 mm in the market because that is not built. So you will, that is not manufactured. So you will get probably 12 mm, 10 mm, and then maybe 12 mm, right? So whatever comes in between should go to 12 mm. And therefore there are standard sections that are built, that are manufactured all over the country, this country, and every countries are there. They have their own standard manufacturing sections. Now, when you add these sections, you get some kind of I section or rectangular section or double I section. What we get? So their details based on what is the height here, what is the thickness here, what is the thickness here, right? What is the width here? All this, based on all this, there is a handbook that is available. We call it Steel Handbook, where all the properties of all different kind of sections that are made in this country are given. Okay, so therefore engineers, whenever they design something, they have to follow the strict, section guidelines. They can add on it. They call build-up sections. You can also make built-up sections. Okay, what are built-up section? If you look at this picture, what does it look like? It looks like a double eye, right? It looks like a double eye. So what is this? This is a built-up section. Okay, you cannot keep two eyes like this. What you have to do, you have to put another steel bracket here, right? So that becomes a built-up section. That means you have taken 2-3 sections and added them together to make a single section. So that becomes a built-up section. Okay. So you can make built-up sections of your own, own ways, as your engineering things required. But those will be part, of this kind of sections, which will add up to built-up section. Okay. So it is important to understand the properties, how to develop the properties of this kind of sections. Mainly the geometric properties. And the geometric properties depend on the cross section. For example, IZ, neutral axis, IX, IY, whatever you do, are all part of neutral axis, are all part of geometric sections. And you need to find out these geometric properties. Okay, so go through a book. A book will also have towards the end some of these sections given and their properties given. Not all, but some. Any book that you take towards the end, yeah. So some of them are given. There are channel sections. There are angle sections also. So this is an angle section. Okay, L kind of thing. So this is an angle section. That is also used. And yeah, so these properties will be given towards the end of the book, any book that you take, and you should go through it, just to see how they can be used in your analysis, and what are the properties that are given, and how do you use those properties. All right, so please go through it. Now, mostly in our class, we will deal with two things. One is rectangular, one is I, and sometimes we will deal with T sections. Other things you can do it. Once you know how to do it for all these three, you will know to do for everyone else. So let's go back and start looking into what we get. So when we are given a beam, its boundary conditions will be given, and there will be some loading that will be given. Okay, some W per unit meter. W kg per meter or Newton per meter, something will be given to you. What you will be asked? You will be asked to find its maximum shear stress and maximum bending stress. Now these two may not be in the same location. They can be at different locations. For example, a simply supported beam will have maximum bending moment here. So its maximum bending stress will be in the center of the length, but maximum shear stress will be at the boundaries, because the boundaries carry maximum shear force, right? No matter what you do, as long as you are in a linear zone, your stress distribution for bending should look like this, and your stress distribution for shear should look like this. And the formulas that you're going to use are very simple, and two formulas. That is, one is My by I, and the other one is Vq by Ib, with Q being first moment of area above the point where you are looking at, right? So if you are looking at Y, it's the first moment of area above this. So it will be not that way, it will be like this area. So these two formulas you have to remember. But while doing these two formulas, you need to go through a lot of geometric properties of the beam. What are the geometric properties that are needed? Geometric properties that are needed is you have to determine neutral axis. And the second is second moment of area. Neutral axis is written as Y bar, and this is written as I. Okay, it might be IZ, or it might be IX, or it might be IY. In books, it will be written as Ix and Iy. Okay, cross-sectional properties. Now let's look at. Okay, so we have to do some stress variation. Okay, let's do a stress variation. CS stress variation. This is what I said I'll do, right? Yesterday, CS stress variation. Let us consider a T section. Okay, let us consider a T section. Let's say this is 10. This is also 10. Let's say this is, oh, that's given, right? Okay. Let's say this is, what do I write? 30. And this maybe I will write again, maybe 30. Is that okay? And that's 10. All dimensions are in mm. Okay. So whenever I write this is all dimensions are in mm. All right, all dimensions are in mm. Now what we have to find first is we have to find neutral axis, right? To find its shear stress variation, we need to know where is the neutral axis. Find we need neutral axis, y bar. And how do you find y bar? We have dealt with this before. How to find y bar? Y bar would be found. Let's say we look from bottom axis, right? Let's say we look from bottom axis. Then how do you find? Can anybody find neutral axis quickly and tell me what would be the value from the bottom side? It will be 10 into 30 into, okay, let me write the formula first so that we remember it. A1 y1 bar plus A2 y2 bar divided by A1 plus A2. So that's going to be A1. Let's say A1 is 10 into 30 into y bar is going to be 30 plus 5, 35 plus A2 is 10 into 30 into this is going to be 15 divided by 10 into 30 plus 10 into 30. Can anyone calculate it quickly? So I can take 10 into 30 common and that cancels. So it will be 35 plus 15 by 2 equal to 25, right? Mm from bottom. Is that correct? Yeah, thanks. Very nice. Somebody has done it. So the neutral axis is passing through this point. Neutral axis, right? Okay. And we know that the shear stress is going to be maximum at neutral axis. Shear stress is max at neutral axis and 0 at top and bottom layers. Okay, so we have done this. Now we have to do VQ by IB, right? Shear stress is given by VQ by IB. So let us calculate. Shear stress tau VQ by I, B. Okay, let's say B is something around 10, 15, whatever you want to say. Now V, comma I, comma B are constant, right? At a cross section. What is left out? Only Q. And Q is, we know, is integral of y dA from whatever point you are looking at to the neutral axis, right? Now let's do this. Now we have here two cross section. One is like this. There are two portions of the cross section. If I look into the top portion, so this is one of the box section, right? It's a rectangular section. And we know for a rectangular section, it's going to be like, how is it going to look like? It's going to look like a parabola, right? So it will vary with y square. Now at the top, so let us draw it here. You draw a line like this, and then you draw a neutral axis. This is my neutral axis, okay? Sorry. And then this is my top layer. This is the layer where there is a change in cross section. And this is the layer, the bottom. At the top layer, it's going to be 0. At the bottom layer, it's going to be 0, right? And it's going to vary in a parabolic fashion in a rectangular cross section. So let's look at this point. This point is 0. Let us look at this point. What would be its value at that point? You know, Q, let's say this is point, this is point A, this is B, there is a B here also, right? This is B1 and this is B2, and this is point is C and this point is D. Okay, so this is B1 and that is B. Now at A it is 0, QA equal to 0. QB, we have to find what is QB1. What would be QB1? QB1 would be area above B1, right? So this is the area and its arm length with respect to the neutral axis, right? So it's going to be, can anybody do it quickly? It's going to be 10 into 30 into, what should this be? So from here to here, this is 25, so that is 40, so this is 15. So 15 minus 5 is 10, I think. This is 10 mm. Is that correct? So that's going to be 10. So QB1 is 10 into 30. Yeah. What about? Yes. And what about QB2? That is also going to be 10 into 30 into 10, right? Anybody? Nobody is doing anything? Nobody has written something here. So I suppose this 10 is correct. So there is 5 here and then the 5 here. 10 is correct.
Sir, I have a doubt at QB2.
Why?
Sir, shouldn't we take two sections at that point, QB2 plus and then QB2 minus, because it won't be continuous.
QB2 plus and QB2 minus. Yeah, so B1, so that's what I did. B1 is in the T portion, the hanging portion. B2 is not in the hanging portion. It's in the narrow portion.
Yes, sir. So it won't be continuous, right?
No, it's not continuous. It's not continuous. Now let's look at QC. QC you can do, right? You have to do, you have to find the neutral axis. So this one plus this one, it has to come. So you can do it. and you can do QD. QD is going to be 0 again. Now, point is V, now we have to calculate tau, right? So tau at A is V into Q at A by I B at A should be equal to 0. Okay. Now tau at B1 is equal to V into Q at A, Q at B1, right? I into B of B1, which is going to be equal to V by I into what is Q? So let's write it as QB1 itself, not a problem. By what is your B there? Your B is 30 there, right? Right? And tau at B2 is equal to V by I again, and Q at B2 by B at B2. So V by I into what is Q at B2? It's again QB1, it's the same value, but your B2 is 10. Okay, so this says tau at B1 is much smaller than tau at B2, and there are other things you can find out. So what happens here is it is 0 here, then let's say this is your tau at B1. So it will go parabolically like this, and then it will jump to a value which is tau at B2, and then it will go maximum here, right, at the neutral axis, and then it will drop down. So that's your shear stress diagram for this T section.
Hello, sir.
Yes.
So we can calculate it anyway, right? Means from D also we can calculate, right?
You can calculate from the bottom side, you can calculate from top side, any side, no problem.
Okay.
So this is going to be yes test. You can see there is a small discontinuity here, as you know, you already have predicted there will be a discontinuity. There is a discontinuity. This discontinuity is due to change in the B or change in the width of the cross section. So wherever there is a change in a cross section, there will be jump in a shear stress. Okay, right, and shear stress will be maximum at the neutral axis because y is 0 at neutral axis, right? Now Q at C is going to be maximum. Now let's again go to a little bit different I section. Let's say we look at I section now. Okay, so we're looking at an I section, and now from whatever you have studied, whatever you have learned already, you can draw the shear stress directly for this. The values you can calculate and give later, but we can directly write the values. Where will be its neutral axis? The neutral axis is going to go through the center, right? And as we know, in this point is going to be 0. This point is going to have some value. There will be a change here, then there will be a change here, then there, and this is 0 again. So that is 0 and this is 0. Shear stress here are 0. And then there will be a small value here, right? Same, there is a small value here. Then there will be a jump. There is a jump. Let's say the jump is up to this point. And then there will be maximum here and then come down. So that's your diagram for shear stress distribution. For an I section. Okay. So if I give you any section now, you can draw for that, right? So you can draw for a channel section. If I give you a channel section and angle section or a channel section looks like this. Okay. You can draw your shear stress distribution. All right, so that's one thing that we need to cover today. So you learned how to draw shear stress distribution for different kind of sections and how to calculate them, calculate Q and calculate shear stress, so that the distribution is known. Axis and another moment of inertia. These are the two things that you have to find when a given section. And we discussed about this probably, how to find neutral axis of a channel section. Like this is a C section. So you divide that C section into different parts. So one part is this, two part is this, third part is this. And then you find the neutral axis based on either the top layer or the base or bottom layer. Okay. So each of the layer is a rectangular. Each of the different parts, sub parts that you have is a rectangular part, and its neutral axis will go through this line of symmetry. So you have area 1 being y1 is t by 2. This thickness is t. So y1 is t by 2, is 6 mm, and then a1 is, you know how to calculate a1, is b is the complete depth minus 2t. Each of this is t. So b minus 2t into t. So that's your area. Similarly, find area 2 and area 3, and finally your neutral axis is going to be summation of ai yi divided by ai. You do this, you will get neutral axis. But you have to remember you are getting neutral axis from a location. So you got neutral axis about this z position, and you see the neutral axis is 61 point something. So here, somewhere. Yeah, somewhere near to this, maybe this one. Okay. Now, one point to note is you will not have single neutral axis in a cross section. You will have two neutral axes in a cross section. So let's look here. There will be two neutral axes. If you have a rectangular beam, it has a neutral axis like this when the moment is going like that, right? But if you have moment about this axis like this, then you have to look into neutral axis, which is this one. Neutral axis always passes through this symmetry of the line. Okay, and two neutral axes will be always perpendicular to each other. Remember these things, don't forget. Where do I write? Okay, let me add on the page here. Neutral axis passes through symmetry or lines of symmetry. 1 point, second point, two neutral axes be to each other. Okay. So you look at this, this is a rectangular beam. So it has two lines of symmetry. One is this, the other one is this. So its neutral axis is going to be, one of the neutral axes is this one, the other neutral axis is this one. So whenever, as I said, whenever looking at a moment which is this one, right, a moment of this kind which is about ZZ axis, you have to look into neutral axis of ZZ. When you look at a moment about YY axis, you have to look at the neutral axis which is line of Y, line symmetry of Y. This I section will also have a symmetry. This is one neutral axis, the other one will be this one for a different bending. For a double section also, this is the line of symmetry, so that's going to be its neutral axis. T section is not a symmetric section, right? Vertically looking, it's not a symmetric section. So its neutral axis will be passing through more where there is more area, right? Since you are doing, you are doing an area moment. Therefore, wherever there is more area, the neutral axis is passed towards it. So neutral axis, instead of passing from the center, it has moved a little bit upward because the area is more towards the upper side. Now this is again a box section, which is a symmetric section. So it's very easy to find neutral axis here. Channel section is also very easy to find its horizontal neutral axis. But for vertical, what you have to do is you have to see which area is more. So this part is more area, right? So it will shift from the center to this way. And you have to find this C value, which you have seen how to find here, right? This is a channel section. For an built up I section where top portion is a little bit more heavy, area heavy, your neutral axis will not go through the center, rather it will move a little bit upward here. So these are the common things that you have to learn and you have to understand. For an I section, for an angle section, it's going to be something like this. Okay. So do practice how to calculate neutral axis for different kind of sections, and also understand physically, from geometry, that whether you are doing it correctly or not. The other thing that we need to find out is moment of area. Second moment of area. I hope you have learned second moment of area in your engineering mechanics class. If you have not learned, please write it in the chat that you have not learned. Okay. No, you can write no, I have not learned, or no, I don't know. Then I will record a video for how to calculate moment of inertia and upload it for all of you. You can calculate second moment of inertia based on various ways for sections that are built up. For example, on I section. For a rectangular section, very easy. It's 1/12 BDQ about the neutral axis. Whereas for I section, you have to calculate it for different versions, right? So you first assume it to be a bigger rectangle. So that's your bigger rectangle. Then you subtract the smaller rectangle from it. So this is the smaller rectangle that is subtracted. Then you add up this section here. So then you add up this section. That is one way of doing. Other way of doing, you calculate neutral axis I for this, you calculate I for this, you calculate I for this about their own axis, right? And then transfer them to the neutral axis that you have for the overall section by using a BD square formula, right? A into D square formula. So that way also you can do. If you are hesitant how to find second moment of area, if you don't know, please write to me. I will definitely take a class. Take not a class, upload a video on this. Okay.
Sir,
Yes.
sir, in the previous slide you wrote IZZ, right? That is second moment of area, not moment of inertia.
This section. Yeah, second moment of area. Yes.
Okay, sir.
Right. Okay. Now first problem. So this is a simply supported beam. Okay, with a UDL acting on it. So the UDL is 20 Newton per meters. And the length of the beam is 5 meter, and its cross section is a rectangular cross section with a 200 mm at the base and 300 mm at the depth. So width is 200 and depth is 300 mm. We have to determine the maximum bending and shear stresses. It's not difficult. So maximum bending stress will be at a location where you have maximum bending moment, okay, BMD. So that right here. Maximum bending stress is at this section where BMD is max. Maximum tau is at the section where SFD, okay, BMD and SFD. So now if I draw BMD and SFD for the structure, I can see that SFD is maximum at the boundaries, where BMD is maximum at the center. So when I design and check it, I have to check for the maximum value, right? If it is safe at maximum value, it will be safe for any other values. Okay. So my maximum bending stress will be section here at the center, and maximum shear stress will be at the boundary sections. So if you calculate the values, your maximum bending moment is WL squared by 8 at L by 2, where your shear is 0, and maximum shear will be at 0, x equal to 0 and x equal to L, and its value will be WL by 2, where the moment is 0. Now, next job is to find the geometric properties of the circle. So first job is to draw bending moment. Second job is to find the geometric properties of the section that is given to you. So for me, it's a rectangular section, and therefore I know its geometric properties easily. So its neutral axis is going to go from the center. That means h by 2 from the top or from the bottom, same thing. So it will be 150 from top or 150 from bottom, right? And its I is 1/12 BDQ. B is 200 and D is 300. So 1/12 BDQ you can find, and you can write the values here. Since the loading is acting here and it's symmetric, so this is my loading and it's going to bend about Z axis. So I have to find only IZZ. Okay. So I found IZZ. Bending stress, determine bending stress now. How do you determine bending stress? I have to determine bending stress at the location where bending moment is maximum. Okay, so that is what written here. Maximum bending moment location I have to find by bending stress. So sigma b is m max by I z z into y max. Remember, my bending stress is always so if you have a beam like this, bending stress is going to be like this, right? So it's always maximum at the top layer. Bending stress is maximum at the top or the bottom layer of the beam. So bending stress will be maximum at the top or bottom of a section where bending moment is maximum. So sigma b max is going to be m max by I z z into y max. Okay, so you put that values back here, and you will get your you put those I z z value back here. You put that w value here, L square value by 8. You can calculate that and put the value, right? Numerical value. Now this is maximum tension as well as compression. Tension will be in the bottom layer and compression will be in the top layer. Okay, but it's same for both because it's a rectangular section. So sigma b max is L by 2 where your shear is 0. Now let's look at maximum shear stress. Is that clear for bending stress? What about maximum shear stress? Maximum shear stress will also have to have V max, right? It has to have a V max. It has to have I mean, which is constant, so I cannot change that. B mean, which is also constant because the rectangular section, I cannot change it, and I have to calculate Q. So since it's a rectangular section, I know that V max will be at the central layer or the neutral axis, it will be maximum. But the location is the boundaries, right? Either at x equal to 0 or at x equal to L. So that is what is written here. What is the value of V at that point? WL by 2. So tau you can put it, and tau max, we know that tau max is going to be at the neutral axis. So you calculate your Q at the neutral axis, which is going to be, as we know, that 1.5 times its average tau. So 3 by 2 into V max by BD. So now if you draw it, this is going to be a section where your shear has to be checked, and that is how your shear stress distribution will be. And this is where your bending stress maximum and that distribution will be something like this. Okay. And these two values for a design consideration should be lesser than your allowable tau and allowable C. This is a simple analysis, right? It's not difficult to do. And all of you can, and how are you going to solve this? I don't have time today. So I'll quickly go through. This design problem says that you have water here, okay? And the water is being held by some planks, wooden planks, which are going like this, right? They're going like this. And these wooden planks are held by some wooden beams, which are this. Okay, so if you see from the top, this is how it's going to look like. So these are the horizontal wooden planks that are going, and the wooden beams are holding them like this. The spacing between the beams is S. Why is the spacing given? Because the water that will hold between two S is going to be used for the design of this beam, because that is the water pressure. We will assume design wise, this is the water pressure that is being held by this beam, and this is the water pressure that is being held by this beam. Similarly, the next beam will also hold some water pressure. So we divide it because you need that area multiplied with the pressure is going to give you the load, right? Now, if you look at vertical section, so this is your beam. So let's forget the planks now. The load that is coming from the water is like this, right? And that will be like this. And this is going to be your spacing S between the beams. Okay. So this is going to be your loading, triangular loading. So once you have a triangular loading, you can find its bending moment and shear force. So bending moment and shear force are drawn here, cubic parabola and square parabola. Once you know the bending moment and shear force, you know where it's going to be maximum. It's going to be maximum since it's a cantilever beam. It's going to be maximum at the fixed end. Okay, so you know the values about the maximum at the fixed end. So you can get those values. Once you know those values, you can find their stresses. Right? In terms of B is not given to me. What has been asked is the maximum allowable is 8 MPa and shear is 4 MPa maximum allowable. Now, once their maximum allowable is given, you can find B for these maximum values. First, you have to check with bending, because I said most of the structures will carry most of the loads for bending. Therefore, you first check with bending, then first to find the value for B for bending, then you check with shear. Okay, so having said that, your maximum value of moment has been calculated, and it will be a hogging moment because it's a negative shear, a negative, it is going to be more on the top side and less on the bottom side. So compression in the bottom side and tensile in the top. So this is your beam, and if you load it like this, it's going to bend like that. Okay, and therefore it will be a hogging kind of moment, right? So maximum shear also you can find out. Once you know those values, your bending stress maximum, you can find sigma B max is M max by I into B by 2, because in the top layer it will be B by 2 from the neutral axis. It's a square section, so neutral axis passes from the center, and you can calculate it. Now you know that bending max should be less than allowable. So if you do that calculation, you get your B to be something like this. You do the calculation, right? Now you have to do what? You have to check whether this B is okay for shear or not. If it is not okay, then you have to design again for shear. So maximum shear is this, and determination for, so okay. So another way of doing is you calculate B from shear also and see whether which one is maximum. So you calculate shear from this. So B from the shear point of view comes out to be this. So you take either of B max, sigma max or B tau max. In general cases, it will be sigma that will be greater than B tau. You can find B for B sigma and then check for whether it's safe in B tau or not. That's one way of doing. The other way of doing is you find both B sigma and B tau and take the maximum value for your design. Okay. So with that, I'll stop